I'm Ahmed Daud, and in this session, we will see why we can't use linear regression for classification problems, or you can say why we have some a little bit different structure in the regression algorithms as compared to some classification algorithms. Okay, keep in mind that each algorithm have some different structure. Okay, and uh, when we instead we are if we are in the regression case in the when we are dealing with regression problems, we have multiple algorithms and each algorithm have its different structure. When we have to use some regression algorithm for some classification problem, then it cannot be directly used. We have to do some changes in that algorithm, then we can use for classification purpose. Okay, some uh, algorithms are you can say parently are have structured like to solve the classification problems. Then they are, you can say, by nature they are algorithms to solve the classification problems, but we can also use that type of algorithms for regression problems. Okay, in other words, you can say you can some algorithms, you can some classification algorithms you can extend to solve the regression problems, and some regression algorithms you can extend to solve some classification problems. Okay, so what type of classifications problems we usually face? A very simple classification problem I will discuss here, and keep in mind I am repeating here that in the we are here dealing, and a couple of sessions we that we will cover. In that these sessions we will consider binary classification, in which we have just two classes in our target variable, uh, in the form of 0 and 1 most probably. Okay, so why we are first learning binary classification, because if you will have a strong grip on binary classification and how the algorithm works in the case of binary classification, then you will see that you can easily grab the concepts about the multi-class classifications also. Okay, so first of all, what type of problems we usually have, or you can say what type of classification problems. Let's say this is data set which has very less number of points. Here I have screenshot of just 10 points, but actually data set also have just 26 points, just only 26 data points. Okay, so here we have just 10 data points. Okay, so this here you will see that the problem statement is here is we have a data set which is explaining, let's say we have 24 samples, so explaining the data set and describing the data about 24 persons. Okay, each sample is representing a person. Okay, let's say this zero sample is representing here a person which is having age 22 years, has not bought insurance. Okay, a person having uh, 25 years age has not bought insurance. Okay, person having or person of 47 years old has bought insurance. Okay, so in this way you have seen that we have a data set of the persons that have bought insurance or have not bought insurance. And here our the explanatory variable or particular here or independent variable is just one variable. On the basis of that variable we are explaining our target variable which is bought insurance. Our independent variable is just one, which is age. On the basis of age we are describing that about insurance, either the person has bought insurance or not. Now on that model we have to train us a classifier or classification model that can predict, by taking some age as an input, that can predict that either this person will buy insurance in future or not. Okay, so that type of problems we usually have in classification scenarios. So Now come back and try to discuss and explore why we can't use linear regression for classification problems. Okay, so we have discussed that in the regression problems we have target variable that are continuous that have been continuous values, but in the case of classification we have uh, discrete values, or you can say we have a categorical target column that we when we are dealing with let's say we are when we are you can say uh, doing coding and we have to feed the data to our model, then we of course we convert our categorical target variable into some discrete values, like here about insurance. There can be like values in the form of yes and no, but here it is converted into form of binary uh, values like 1 and 0. Okay, so although in the case of regression problems we usually have continuous values, and in the case of the classification problems we have categorical values. Okay, like here in the form here we have two categories, 1 and 0. Okay, so some of you can argue that if we have just two values, 1 and 0, and which is of course a numerical value, uh, although these are discrete, but actually these are numerical values, some of you can argue, then why we cannot use linear regression for that problem. Let's say if we some of the person that is asking me can ask me that if a linear regression we will train on that data set, and if we set some threshold in that way that linear regression will give some numerical value against each age, and if the value is closer to 0, then we can say the person that this person will buy out insurance, and if the output of linear regression model is closer to 1, then this can be a 1 class. Okay, then the result can be 1. Okay, some of you can argue in that way, and some of maybe of you are thinking in this way that if we will train linear regression model, it can also can work here. Okay, like in this way, if uh, if you will train a linear regression, and if the linear regression is giving the values closer to 0, let's say 0 0.1, 0 0.2, 0 0.3, 0.41, 0.23. Let's say you have set a threshold like you have just two classes, you have just two classes, 0 and 1. Okay, and you can set a threshold as it is between it is either the result should be either 0 or either 1. Okay, and you said that you have set a threshold, let's say threshold you have set a threshold 0.5. It means that if your value is less than 0.5, or you can say your output is less than 0.5, means it is closer to 0, then it is 0. It can be predicted as a 0 class. And if output is greater or equal to 0.5, then can be predicted as 1 class. Okay, this can be an argument. Okay, uh, that how we can use that we can use linear regression as a some for some classification problem. Okay, so by considering your argument, let's try to build a linear regression model upon that classification data set. Okay, on that data set, try to build some linear regression model. Okay, or you can say regression model, and we will see what will happen. Okay, upon your request, upon your argument, I have here trained a linear regression model. You can see here. This can be this way. Okay, you can see that this is a linear regression model, linear regressor. You can say this is a linear regressor. We have actually this data set, in which we have about 24 data points, and sum of data points, like here you can see here, 5 plus 5. Okay, we have 10 data points, these are, and 7 plus 5, and these are 12 data points. Okay, total we have 22 data points here. Okay, if you will plot a scatter plot in this way, then you will see that your scatter plot is showing that 10 data points having a 0 as a output and 0 label, and 12 data points has a 1 label. Okay, and you can see that all data points in one line because these are the 0, and you can understand that because these are discrete values we are having in our target column, we have some categories, so that's why these are in this way. These are representing 0 class, and these are representing as a 1 class. Okay, so if we will plot, or we will train a linear regression on these data points, these let's say 22 data points, which are having a discrete uh, output, then we will have a linear model like this. Okay, like this is this blue one, this blue one. We have this is this blue line is a our linear model. Okay, now you have set a threshold like here, uh, in between this is 0, this is 1, this is 0.5, and you will see on which value our model is giving the value exactly equal to 0.5, and you have seen that it is giving at when the age is equal to 38, our linear regressor is giving 0.5. Okay, so here you have you can say write a logic in that way. If the age is greater than 38 or age is equal to 38, then your bout insurance, your value on the y-axis will be equal greater or equal to 0.5. Of course, if your values are on this side, you will have some higher value on your regression model, and you will have output greater than 0.5 or equal to 0.5. Then it can be considered as a one class. And if age is less than 0.38, then your boat insurance, or your you can say output, or the value on the y-axis will be less than 0.5, and can be categorized as a zero class. Okay, so for simplicity, we can understand in that way. Okay, so linear regression is working here. Now, what is the problem? The problem is here, if your linear regression will give you output. Okay, so if your linear regression will give you the output in between 0 to 1 range, then you can set a threshold of 0.5, and you can classify in that way, that if there is output is greater than 0.5, then it should be, it will be closer to 1, and it can be classified as 1 class. And if your output is less than 0.5, then it will be closer to 0, and it can be classified as 0 class. But if your output will be greater than 1, what will happen? Let's say here you have age, let's say 60. Against 60, you will have here your linear regressor will predict the value, let's say 1.15. Okay, which is greater than 1. Now what will you predict for that? Here in that case, when your age is let's say here your age is 15. Okay, if your age is 15, your linear model is predicting here, is giving a value, let's say 0 minus 0.09, let's say. Okay, now it is also less than 0. Okay, now if your output, your predicted value, if your predicted value if your predicted value in case of linear regression model, if your predicted value is greater than 1 or is less than 0, then what threshold you will set. Okay, here you can see that this value 1.15 is not so much greater than the 1, and you can argue here 0.09 is not so much greater less than 0. But when you will it's a very simple data set. When you have some complex data set and some other values or some other type of independent variables also you have in your data set, then you will see that some you will get in case of linear regression model very high values on both ends. Okay, and you know linear regressor and linear model have no limit, it can give you any value. Okay, it is not bounded in the range between 0 to 1. It can give you any value, let's say 400. Let's say if your model will predict the value 400. Okay, what you will do. Okay, if your model will predict value let's say minus 200, what you will do. Okay, how you can set a threshold. You can set a threshold only the case when you have and your model is predicting the value in between 0 to 1. Then you can set a threshold that if your value is in 0 and 1, your model will give the range output in range of 0 to 1. The middle 0 1 is 0.5, and if the value is greater than 0.5, can be considered as closer to 1, is classified as a 1. If the value is less than 0.5, then it is closer to 0, considered as a 0 class. But if your model is not giving you the values in between that range, in the range of 0 to 1, then you cannot estimate either it is close to 1 or either it is close to 0. Okay, so it is also difficult in the case of setting a threshold, and it is also very difficult. Let's maybe you can argue in the case of threshold, but it is also not a good case that your model is giving very high values, but your output is just 0 and 1. Okay, so this is one of the problem of linear regression, that it have no limits of predicting value. Okay, so the second problem we will discuss here. The second major problem in is problem of linear regression. If we will use this linear regression model for the classification problem, then what will happen? Let's say if we have a uh, extreme value, let's say there is a person who is having a age about 98 years old. There is a person who is 98 years old, and of course the boat insurance is also equal to 1 for that person. Okay, so you can see all of that all of your data is less than about 62, and all of other data points are less than 62, having age value less than 62. But there is also another value in the age column which is 98, and of course it has about insurance is equal to 1. Okay, so in your data set you have extreme value. What you will do in that case, what your linear regression model will do in that case. Now you will see here, you will draw a linear regression model, and you know about the training process of linear regression. You know linear regression works in that way, it tries to minimize the error for the sake of becoming a best fit line or best fit model. It try to decrease the prediction value and actual and the difference between actual and prediction value. It try to decrease that difference. Okay, so here you can see here, just due to one data point, your model is rotated a little bit in clockwise direction. Okay, you will see in that case very clearly. This is a model, linear regression model. This is the linear regression model. This model when you have no extreme values. Okay, but when you have just one extreme value, your model is rotated a little bit in the clockwise direction. You can see here here it is passing from these data points, but here your model is passing from the last two data points. It means your model is treated in this way, just for the sake of to decreasing the error. And here you can see here your model is previously without extreme values, your model is passing in from these three data points, but now it is passing from last 2 points. It means it is rotated in this way also, okay, towards that data point. Okay, you can see that your model is rotated a little bit in the clockwise direction, just due to one extreme value. What can happen with that? The resulted output and resulting model can also cause uh, in the can also result in the a lot of misclassifications. Okay, it can give you output values. Let's say here we have just 24 data points, a very less number of data points. That's why there is let's say 1 second. Let's say here again it is okay, for simplicity I can try here in this way. Okay, for now you can see here there is no misclassification here, but when we you have multiple data points and a lot of data points in your data set, when your model is rotated sharply in that way just due to one outlier, maybe in your data set you have multiple extreme values. These are not actually the outliers, these are the extreme values of your data set. Okay, you can also not exclude these type of values, and due to these extreme values your model will rotate it a lot. When your model will rotate a lot, or your model linear regression model will rotate a lot, it can result in the way that there are a lot of data points can be have value less than 0.5, but they are actually one, they are having label as one. Okay, it means it can result in that way it will predict the probability of the value less than 0.5 for the samples which are already have uh, the result or the true value 1. Then either your model, because of your model is giving the value less than 0.5, so that's why you will classify it as a 0, but actually its true value is 1. In this way you will misclassify, you can misclassify a lot of data points. Okay, just due to your model, and just due to sensitivity of your model towards the extreme values. Okay, so that's why linear this is also a great you can major problem in the linear regression if we will use it as a classification or for the classification problem. Okay, so you have seen two major problems here. One is that your linear regression do not squeeze your output in between 0 to 1. And the second problem is here that it also much sensitive to outliers, and it can also result in the a lot of misclassifications. Although there is we are not getting here misclassifications, but there can be a chance, because here we are discussing very simple data set, but when we have a data set where having large values and large number of columns can result a very uh, large number of misclassified data points. Okay, you can also see a lot of you can test linear regression model on different data sets available on the internet. You will get an idea that how much type of results it will give. Okay, so by discussing that to use a linear regression for the classification problem, you got an idea that it has two flaws, and you are getting a hit in your mind, and that and you also got an idea why we have studied logistic function, and you are most of you are recalling and have recalled the characteristics of logistic regression, logistic function, which actually squeeze the output in between to 0 to 1, and also uh, it can also uh, not sensitive too much to the outlier. Uh, the reason is that you have got an eye when you will again recall your logistic function, you will see and you will understand that as your model is having the value closer to infinity, your model is giving the value output as closer to 1. Okay, and you will see that your model will rapidly reach towards the 0.8 or 0.9, but to reach towards the 1, very large values, very large values will you can say increase the output a little bit. Okay, in other words, you can say your logistic function is not sensitive to the extreme values. Okay, so now we will apply our logistic function on the linear regression model's equation, and we will convert our linear regression model into logistic regression model. As we are converting our linear regression model into logistic regression, or as we are converting a regression model into some classification model, that's why we call it as a we have a regression name in our classification problem, in our classification algorithm. Okay, this is logistic regression. Okay, and it is a classifier. It is classifier. Classifier means model for classification problems. As this model is converted from the regression model, that's why we have regression in the name of that classifier. Okay, and as we are using logistic function to convert regression model into classification model, that's why the logistic in its name. So that's why by combining logistic function and linear regression, you can say you are getting logistic regression. Okay, how we can apply our logistic regression function on the linear regression models equation, we will see here. Okay, your models equation, your linear regression models equation was like that: y cap is equal to mx plus c. There can be multiple notations. I have explained multiple times that you can write in this way: theta 0 plus theta 1 x1. You can write in that way like sigma theta I x I, and I will start from 0 to m. M can be considered number of features, and starting from 0, it means theta 0 x 0. Theta 0, you know, it's an intercept, and x 0 we have fixed here as a 1. Okay, so we can also represent our equation in that way. Okay, so you know about and I have explained multiple times, no need to here again explain. Okay, so this type of equations we have, this type of equation we have in case of linear regression, and we say that this is our model, and we have to calculate these parameters to get a best fit line. In case of logistic regression, we will because here you can say this y cap have no limit. Okay, it can give you any value from minus infinity to positive infinity. Okay, and it also depends upon the case. Sometimes we have you can say non-negative values in the output, but I am giving you the generalized idea that it has y cap having no limit. It can uh, give you any value. Okay, just because of the reason that it can give you a continuous value in any range. Okay, the because just because you have your equation like that. Okay, as you are changing your x, your y cap is changing here. Okay, if you will apply a logistic function on that y cap, or you can say on that, if you will apply logistic function on mx plus c, you will get the logistic, or you can say equation for the logistic regressor. Okay, how you will see here. P is equal logistic mx plus c, and when you will apply, it will be in this way: 1 over 1 plus e raised to power minus. We have seen in the logistic uh, functions case that we are having in this way: p t 1 over 1 plus e raised to power minus t. Okay, but here as t is mx plus c, so that's why it is mx plus c. Okay, and you can rewrite in the form of log odds, and you know about that, uh, log of p over 1 minus p is equal to mx plus c. And sometimes you people will call that log of odds is linear. Here in that case, log of odds is linear just because it is an equation of linear line. Okay, so here you can see this is the most clear. Log of odds is equal to mx plus c. Okay, now this p, which is of course that's why I have given you a hint why I am using here p notation instead of y. The reason is that it will give you a value in between 0 to 1 and can be considered as a probability, um, because it is in between 0 to 1. So that's why I'm using here the p. Okay, you can use here p cap also. P cap. Okay, p cap always be in between 0 to 1. We got an understanding because we have applied logistic, you can say logistic function on the equation of linear regression model. Okay, so now if your p cap will be greater, or always know your output will be in the range of 0 to 1. Now, if you can set a threshold, if your output is greater than 0.5, then you will consider as a one class. And if your output is less than 0.5, you can consider as a zero class. In other words, if you want to write in the form of y cap, your logistic regression equation, you can write in this way. Your y cap will be 1 if your probability, it's a p over 1 plus e raised to power minus mx plus c if we have just one variable. Okay, so if your probability is greater than 0.5, it will be 1, and if less than 0.5, it will be 0. Okay, now this is your logistic regression. You have converted your linear regression equation into logistic regression. Okay, now the second advantage of logistic function is that it is not much affected by the outlier. I have told you, and you can see also from here very clearly that in the case of linear regression, your model is rotated a little bit in the clockwise direction. But here you can see in the case of logistic regression, when you have a extreme value here, you have extreme value here, but your model is not much affected by extreme value, and it is giving you the same type of curve as in the case of no extreme value, and same curve as in the case of extreme value. Okay, you can say that this is logistic function is not much affected by the outliers. That's why we are using here logistic function to convert our linear model into some classification model. Okay, so that is all about the today's session. We have discussed that why we cannot use linear regression model for the classification problem, and how we can convert our linear regression into some logistic regression, the equation of linear regression into some equation of logistic regression. Why logistic regression is called have regression in its name. Either it is a classification algorithm, but it has a name regression in its name. Why it is called logistic? The reason, because it is using logistic function. You got all about the logistic regression. Now you also have the equation of model, or you can say that you also have learned the equation of logistic regressor. In the in the next session, we will try to discuss or learn how we can train that model, how we can train that model. And I will recommend you that you should also you should study and have a look before the next session on the training session or training part of the linear regression. Okay, so because in the logistic regression we have different equations, so we cannot use the same type of process that we have followed in the case of linear regression. Okay, for the training case. In the next session, we will see how we can do training of our logistic regression. So for now, thank you.